So using our knowledge of vertices and edges, let's start thinking about how we could come up with sort of a curved shape, right? So a polyline might be a good way of going about doing this. So with a polyline, we simply have a set of vertices connected together by some edges or line segments. So we could have a whole bunch of vertices here and just connect them together with some edges. All right, so this is a decent start to modeling a perfectly curved surface. However, this polyline is defined explicitly. That is to say that it is defined at a specific resolution. We only have a certain number of vertices here, and to get this polyline to be any smoother, we would have to subdivide it. Right? We would have to subdivide it, start introducing new vertices, and then we'd have to smooth everything out to, right? We'd have to smooth out the position of the original vertices to start getting a smoother curve. So this is where splines come in handy. Splines, on the other hand, are defined implicitly through an equation. By solving the equation at different displacements along the curve, we can obtain as many points as necessary to render the curve at sufficient resolution. Multiple curves can be connected together to form a longer path. So just to be clear here, the equation which defines this curve is going to allow us to solve for the position of any point that falls on this curve. So perhaps we could look for the point at exactly halfway along the curve, right? So we'll see in a second that we call this parameter that we vary over the surface or along the length of the curve. We call this parameter t. So for t being equal to 0.5, right, that'll be exactly halfway along the curve. So we can actually solve for this point and figure out precisely in this case, we are working with two-dimensional coordinates. We can figure out exactly where in two-dimensional space this point is. We can do the same for t equals 0.25, right? Which would allow us to find this point right here, about a quarter of the way, or I should say precisely a quarter of the way along the curve, right? We can do this for any point along this curve. All right, so the first type of spline that we're going to talk about is the Bezier curve. So a Bezier curve is a type of parametric curve used very frequently in computer graphics. Bezier curves are defined by two or more points, as well as a value t, which ranges between the values of 0 and 1. So there are different types of Bezier curves we can draw, and we're going to start with the most basic type, which would be the linear Bezier curve. So this curve will be defined by P0, which will be a point sitting at 1, 1. And so let's draw that in there. 1, 1, this is going to be P0 right here. And we will also have P1, which will be a point sitting at 3, 4. That'll be at 1, 2, 3, and 1, 2, 3, 4. So this point will be right around here. That'll be P1. Now, the visual intuition for drawing Bezier curves is fairly straightforward. And again, it's going to be quite trivial for working with this linear Bezier curve. However, we'll see that the same rules that we can use here apply to a Bezier curve of any complexity. So all we have to do is draw a straight line between each set of points. And then we're going to introduce this t value. Remember, I said a Bezier curve is defined by a set of points as well as a value t, which varies between 0 and 1. So let's start with a t value of 0.5, and let's just plot out a point that we'll just estimate about halfway, right? About 50% of the way along this line, this imaginary line we have drawn between P0 and P1, right? So there it is. There's t equals 0.5. We can also do the same thing for, let's say, t equals 0.25 and t equals 0.75. And again, this is trivial to do, right? So, right, this was about 0.5. This would be 0.25, about a quarter of the way along, and this would be 0.75. All right, so by connecting these points together, we can draw the entirety of the Bezier curve. So super simple and straightforward, of course, because it is a straight line. However, we'll see the beauty of this very simple set of rules for just drawing out the curve that we can use for more complex curves. Before we move on from this section, let's just quickly solve for a single point along the linear Bezier curve. And so we'll use t equals 0.5. We'll solve for this point just to see exactly how that works. All right, so the equation for the linear Bezier curve is fairly straightforward. So b of t will be equal to 1 minus t times the component of 0.0 plus t times the component of p1. And of course, we are going to have to solve this equation twice, one using the x components and a second time using the y components of our points, right, in order to get x and y components for the resulting position. All right, so let's just quickly go right ahead and do this. So let's start by using the x components here. So b of t is going to be equal to 1 minus, we are using the value of 0.5 for t, so this will be 1 minus 0.5 times the component, the x component in this case of p0, so that is 1 plus t, so that is 0.5 times the x component of p1, which is 3. All right, so quickly solving this here, 1 minus 0.5 is 0.5 times 1 is 0.5 plus 0.5 times 3 will give us 1.5, and adding these two together will give us a value of 2. All right, so 2, let me just draw a new point here. This will be, let's call this P alpha. All right, P alpha will have its x component be equal to 2. And then we do need to quickly do this again for the y components. Let's use a different color here. So in this case, b of t, well, b of 0.5 for the y components in this case. Right? Remember, this was 0.5. So b of t will in this case be equal to 1 minus 0.5 times the y components of p0, that is 1, plus t times the y components of p1, right? So 0.5 times, and then we have a 4 down here, times a 4. All right, so again, quickly solving this, we have 0.5 plus, and 0.5 times 4 is a value of 2, and so adding these together give us 2.5 for the y component. Now, let's just plot this real quickly. Let's plot point alpha, just to verify that we did this correctly and that our intuition, our visual intuition for drawing the Bezier curve makes sense. So let's just move this a little bit closer so we can see what we're doing. And let's just figure this out. So we have 2 on the x-axis and 2.5 on the y-axis. And well, I mean, my drawing isn't absolutely perfect, but it is close enough. And we can see that the visual intuition does work, and that by solving the equation for t equals 0.5, the resulting point P alpha, sits exactly halfway along this curve. All right, and next we have the quadratic Bezier curve. So the quadratic curve is defined using 3 points. So we'll define those. We have P0 again at 1, 1. We will have P1, which will be sitting at 3.5 and 2. And finally, we will have P2 sitting at the position of 3, 4. All right, so let's just quickly plot those points. So P0 at 1, 1. This is P0. We've got P1 at 3.5 and 2. So that is right around here. This is P1. And finally, P2, this will be at 3, 4, 1, 2, 3, 4. So that will be right around here. And that will be P2. All right, and now using the same rules that we used for the linear Bezier curve, let's just draw out this quadratic curve just to get a sense for what it's going to look like. All right, so we do start with those imaginary lines connecting each set of points, and then we are going to try a few different t values here. So, well, let's start once again with t equals 0.5. So using this t value, what we're going to do is take, remember, this is a value varying between 0 and 1, right? So 0.5 is halfway through, or 50% of the distance between the points, right? So there's halfway through each of those imaginary lines. However, because we have 3 points to work with, well, we're going to find that we need to draw a third imaginary line, and also find 50% of the way along this line. And so this point right here, because there are no more imaginary lines to draw, this point will be a valid point for trying to draw out this curve. Now, we might make a few mistakes in trying to estimate where this curve is going to fall, so we'll quickly just use a few more t values here to aid us in drawing out this curve. So we'll also test 0.25 and t equals 0.75 to get, a quarter and 3/4 of the way along these lines, respectively. So starting with t equals 0.25, right? So we start with, about 25% of the way along this first line, 25% of the way along the second line, connect those together, and finally take about 1/4 of the way along this resulting line, right? So this point will also help us draw out that curve. This is a point that will fall on the curve. We'll do the same real fast for t equals 0.75. So there we go. 3/4 of the way. Right, makes sense. And then finally, right around here. And we should do that in this same pink color. All right, so this will help us draw out this quadratic Bezier curve. So now, that's not very good, is it? Right there, good enough, good enough. So now we can get rid of all this intermediate information. This is not a part of the final curve, and we can just, we can see the final quadratic curve in all of its glory. All right, so there it is. And let's also compute the equation for a single point along this curve. Let's find one point, just to, again, get some more experience with solving the equations and to see how that works. So the equation for the quadratic Bezier curve is up here already, ready to be used, right? So we've got a 1 minus t squared times the component from p0 plus 2t times 1 minus t times the component from p1, and adding t squared times the component from p2 on to the end there. All right, so this is the equation for the quadratic curve. Let's use it and let's solve for the x and y components of the point that we're looking for here. Again, we're going to be looking for p alpha. We are going to figure out where this point lands. Now let's actually solve for t equals 0.25 in this case. All right, so we are going to be looking for b of 0.25, b of 0.25, and okay, so for the x components, that will be 1 minus 0.25 squared times 1, right, so times the x component from p0, so times 1 plus 2 times 0.25, and then we've got times 1 minus t, so 1 minus 0.25 times the component from p1, right? So that's a 3.5 plus t squared, right? So that's 0.25 squared times the component from p2, which is our value of 3 there. All right, so quickly solving this, we get 1 minus 0.25, which is 0.75, squared, which is 0.5625, times 1 takes care of that term, plus 2 times 0.25 times 0.75 times 3.5 gives us a value of 1.3125. 1.3125. And that takes care of that term. And finally, we have 0.25 squared, which is 0.0625 times 3, which is 0.1875. All right, so adding everything together gives us a final value for the x components of 2.0625. So that is 2.0625 in the x component. Let's quickly solve again for the y components here. So we can use a different color here. So b of 0.25 for the y components will give us 1 minus 0.25 squared times the y component for p0, all right, the y component for p0, so that is a 1, plus 2 times t, which is 0.25, times 1 minus t, times the y component for p1, which is 2, plus, and then again we have t squared on the end here, so 25 squared times the component from P2, and that is a value of 4. All right, so quickly solving this again, so we have 1 minus 0.25, which is 0.75 squared, so again we have 0.5625 on the end here, plus 2 times 0.25 times 0.75 again times 2 gives us 0.75 for this term, and the final term being 0.25 squared, which again is 0.0625 times 4, which gives us 0.25, and adding this all together gives us 1.5625. All right, so let's put that in here for the y component. That is a 1.5625. Fantastic. All right, so we found our point. Let's move this down here so that we can see what we're doing. And let's plot this just to make sure we didn't make any mistakes and that this calculation does make sense. All right, so we're looking for 2.06 on the x-axis, so just beyond a value of 2, so right about here, and 1.56 on the y-axis, so a little bit beyond 1.5, so how about right around here? And so plotting this point, well, my drawing isn't perfect, but it works nonetheless. And we can see that this is how we compute the location of points which fall along the curve, right, defined by these control points, all right? So there is the quadratic Bezier curve. And finally, let's just briefly talk about the cubic Bezier curve. So the equation for this one, well, it's provided in the notes for this lecture. It's a bit longer, and we won't take the time to solve for any points using that equation. But again, we will just draw out a simple curve, again, just to get a bit of an intuition for how to work with it. So let's just put down some points here. So a cubic Bezier curve makes use of 4 points, right? So one more than the quadratic curve. So again, we could just have some points in our two-dimensional space here. And then we could get an idea of just whereabouts that resulting curve would fall. So again, using the same rules that we've been using thus far, we draw an imaginary line between each set of points, and then let's try and estimate where the final point along the curve would fall for a few different t values. So again, let's start with t equals 0.5. It's always a good place to start. So we get halfway along each curve, connect those by imaginary points, or by imaginary lines. So we take about halfway along each of these imaginary lines, connect those points by new lines. Now in this case, because we have another point to work with, and we can actually draw another imaginary line here. So we're going to go ahead and do that. Again, taking halfway between each of these, halfway along each of these imaginary lines. Make another line there. And finally, using a new color here, we would find the actual point along the curve that we're going to work with. So let's do the same thing for t equals 0.25. And maybe we'll leave it there. We won't spend too much time doing this because we've already seen this process happen a number of times. So 0.25 gives us about a quarter of the distance along each line here. This starts to get a bit complicated. We've got a lot of intersecting lines and such, so yeah, just estimating where this would go. And so there we go, about a quarter of the way along that final imaginary line. All right, so if we were to draw this out, you could see that the resulting curve would look something like that. And of course, we would get rid of all this intermediate information to actually see the resulting curve, right? So using only the positions of these control points, we can define this entire curve. All right, so this is a cubic curve, and this is how most freehand curves are drawn in 3D graphics. So taking the idea of just single curves, we can kind of take this to 3 dimensions and just imagine for a second, well, what if we had, a set of curves which, kind of flowed in one direction, and then we had another set of curves which intersected this set, right, and flowed in another direction, and we turned this into sort of a mesh pattern or a grid. Okay, so I am not describing a polygon mesh here. Instead, I'm describing what we call a Bezier surface. All right, so simply by taking this intersecting set of Bezier curves, we can come up with something called a Bezier surface. We can basically vary this value. In this case, we have 2 parameters. So t, and often the other value is called s. Right, so we can vary t and s along this now 3-dimensional surface, and implicitly define an actual 3-dimensional surface. All right, and so this is pretty much the basis of NURBS objects, which we'll talk about in a few short moments. Before we move on here to the next section, we'll just quickly look at a few other types of splines that you'll run into in 3D graphics, one of which is the Hermite Spline. All right, so the Hermite Spline is a little bit different from a Bezier curve in that, well, we've got some points here between which a curve will be drawn, but we also specify essentially the slope at each point, right? So we also have a vector at each point here, which is going to control how the resulting curve looks, right? So with a slope kind of running in this direction, right? This side of the curve is going to stick out a fair ways, and then with this vector kind of pointing, more in this direction, this curve is probably going to end up looking something like this. All right, so we are not only able to define the path of this curve using control points, and note the fact that the curve does actually pass through all control points in this case, which is not the case for the quadratic and cubic Bezier curves, right? There are points there that the curve does not pass through. However, with the Hermite Spline, we are also able to kind of control the shape of the curve using these vectors at each point. And if we were to connect a whole bunch of Hermite splines together, we would end up with what we call the Catmull Spline, named after its creators. All right, so it's really no more complicated than simply having a number of points, and the curve between each point is simply specified using this direction vector, right? So this vector is going to kind of pull this curve out a little bit, and then as we head into maybe this point, right, this curve is going to get kind of nicely smoothly pulled in this direction. Maybe this one down here is going to continue in this direction, which is going to kind of pull out some parts of this curve kind of closer to the point, and maybe this one goes smoothly off into this direction, right? So basically, by controlling these vectors, by moving them in different directions, we can create bends or twists or sharp details in this curve. And you'll find that animation curves behave this way, or we're able to manipulate these handles on each keyframe to get the curve to do different things. So that is a Catmull spline. It is a collection. It is a set of Hermite splines.